All right, so the recording has started. This is chapter 12, content review. This is going to be also kind of like a refreshing of concepts for the quiz that is on Wednesday, I believe. Might be Tuesday for some of you guys as well, but the PowerPoint slides are uploaded on Google Drive under the Week 12 folder under content review. There are a set of practice problems with their key as well on in that same Week 12 folder under extra practice problems. So you should have hopefully everything that you need to do well on this quiz between the PowerPoint slides, the content review video that I'm doing tonight, as well as those practice problems, right? And then you have practice problems that are in the readings. I think those are probably the best practice that you can get that is most going to be, or is going to be as similar as you can get to the quiz questions, right? So practice problems from the reading, practice problems that I have uploaded on Google Drive, my content review slides, and then content review video to like emphasize or visualize any extra concepts. So that being said, I'm going to get into it. Like I said, this is going to be uploaded to the YouTube within like an hour or two of this session. Just depends on how long it gets to process everything. So, and I'll have a transcript of the video in the form of like captions and stuff on YouTube, and then I'll have a PDF of the transcript on Google Drive as well, as you guys can search through concepts and things that I said throughout the video. But yeah, so just an overview of what this week covers. We're covering magnetic fields, magnetic forces, right? First, we're going to start off with magnetic fields. First things first is thinking about like, what is a magnet, right? What's the basic unit of magnet? So you probably have seen a magnet. You've probably had a lot of experience with magnets, right? So you know that there's a north and a south pole to a magnet, right? Am I sharing my screen? Shoot, hold up. I thought I was. One sec. There we go. Can you guys see that? My bad. All right, so there's the screen. Hopefully you guys can see that. Like I said, for a magnet, you have a north and south pole. If you messed around with magnets without even like knowing any physics, you probably know that the north poles won't go together. They won't kind of attach or be attracted to one another, but a north and south pole will, right? So it's kind of similar to electric charges, electric fields, right? Where you have like charges will repel and opposite charges will attract, right? So like poles will repel, opposite poles will attract. And so this brings us to the idea of a basic unit of magnet, which is a magnetic dipole. You always have to have like a north and a south pole. So if you were to cut a magnet in half, you just keep cutting it in half, keep cutting it in half, you would always just end up with a north and a south pole. You wouldn't end up with just one pole. You always have to end up with both. So the basic unit of a magnet is a magnetic dipole. So if you just look at this, right, and this is north and south, right, if this was kind of like plus and minus, well, if you cut it up, well, then you'd have a minus here, another plus there, right, and a minus here. If you cut it up even more, well, then you have a plus here and a minus there, right, et cetera, et cetera, et cetera, right? You always have to have magnetic dipole as your basic unit for a magnet, and you can see that here in the figure. Now it's also important, like similar to the electric field stuff, to figure out how we're going to draw these magnetic field lines. And if you remember from the electric field like chapter and stuff, right, there's two ways that you can kind of describe electric fields, and there's also two ways you can describe or draw magnetic field lines. So the first way is to look at them with vector field diagrams, and those are that way is a less common way. More common is using the magnetic field line diagrams, but it's also nice to kind of understand this just in case you kind of get it in a written homework problem or online homework or even a quiz or an exam. You never know. So basically, for vector field diagrams, you have the magnetic field, and that's represented as a set of vectors around the magnet, right? So you just have a bunch of these vectors pointing left, up, right, down, right? And so longer vectors in that diagram, the longer vectors, here you have like a shorter vector, and here you have a much longer vector. Those longer vectors indicate a stronger magnetic field at that specific point. And what we realize and what we notice is that the magnetic field, and you can test this out in real life as well, the magnetic field is stronger usually closer to the magnet, right? So the magnitude of the electric field, like strength, is going, not electric field, my bad. Magnitude of the magnetic field strength should be stronger closer to the magnet, right? So magnetic field strength closer to the magnet is greater, right? So vectors are drawn in the direction that the North Pole on a compass would point, right? So we draw the vectors based on how the North Pole of a compass would point. Well, this requires us to understand that the Earth has a magnetic field of its own, right? There's a North and a South Pole to the Earth. Well, a North Pole on a compass, right? A north direction on the compass would actually point towards the magnetic South Pole, right? It would point towards the magnetic South Pole. So I believe, if I'm not mistaken, if I didn't interpret this incorrectly from the reading, but basically the North Pole, right? The North Pole, that is actually the magnetic South Pole of the Earth. And the South Pole is the actual magnetic North Pole of the Earth, right? So if you were to kind of like draw the Earth like this, where you have, like, this is your North Pole and this is your South Pole, based on the normal north and south directions that we know, well, this is actually the this is actually the South magnetic pole, and this is actually the North magnetic pole. And so it makes sense, because if we had a compass and we were trying to point north, right? Well, north would be attracted to the southern magnetic pole, right? So the north, like the north direction, has to be a southern magnet, basically, or a southern magnetic pole, in order for the north direction on the compass to point towards it, right? So we said that like poles will repel and opposite poles will attract. So if I have a north direction here on my compass, it's going to want to be attracted to a southern magnetic pole. Well, if I'm trying to get this north to actually point in the direction north, then I have to know that my Earth, north direction on Earth, is actually southern direction with respect to the magnetic field. Does that make sense so far? Yes, no, thumbs up, thumbs down. Okay, and so you can see that here from the diagram as well, right? Like these red or orange or whatever north poles are pointing towards that south pole, right? Or they're going to be pointing pretty much like in a direction like here, would be pointing directly away from the North Pole. So that red would point away from this red North Pole here, because it wants to be repelled, basically, right? Like I said, we represent the stronger magnetic field near the magnet by longer vectors. So if you're farther away, you have a very small vector, as opposed to if you're closer to the magnet, you have a longer vector, because the magnetic field strength at that point would be greater. We also have magnetic field line diagrams, like I said. These can be represented as lines around a magnet. This is more common, right? It's kind of similar to what you saw with the electric field chapter as well. So, like electric field lines, magnetic field lines, when they're drawn closer together, that's an indication that the magnitude of the electric field, or the magnetic field in this case, is greater. I think I have to edit this to magnetic field. But yeah, magnetic field lines, when they're drawn closer together, that means the magnitude of the magnetic field is greater. So here they're very close to one another. There's not much space between them. And that makes sense because you're closer to the magnetic field, or to the magnet itself, right? So the magnetic field strength is greater when you're closer to the magnet. If you're farther away from the magnet, you'll see the magnetic field lines will be more spaced out. So that indicates a lower magnitude or lower strength at that point. And then if you're wondering about the magnetic field lines themselves, well, they're drawn tangent to the direction of the magnetic field, right? So if you have north, south, here is your magnetic field line, right? And it's drawn tangent to the line, right? So it's along the direction of the line. Tangent just means along the direction of, or adjacent to. But yeah, and then the last important thing to know and understand is that the magnetic field lines will emanate or come from the northern pole and then come into or point towards the southern pole, right? That's kind of similar to positive and negative charges that we had in looking at their electric fields. So remember, a positive charge would have electric field lines pointing outwards, and then negative charges would have them pointing inwards, right? So it's like with electric field lines, we had the field lines coming out of the positive going into the negative. Here we have it coming out of the North Pole and coming into the South Pole, right, for magnetic field lines. That's another important thing to understand here. But that's essentially how to draw or visualize these magnetic field lines in both of those ways. And what's unique or different about magnetic field lines as opposed to electric field lines, right, in some cases, that these magnetic field lines have to make a closed loop. You always have to start from that north pole and then come and make that loop, finish it off to the south pole. And really, it doesn't end just there, right? What happens is that it comes in through here, goes into the south pole, and then kind of goes through the magnet and out and back again. So here's just that loop right there. So these magnetic field lines always have to have a closed loop, as you saw in that last image, right? Field line must come back onto itself. Now, this chapter also wants to address something really important, which is kind of trying to go back to the last couple of chapters, which is looking at current coming through a wire. What's unique about that current going through that wire, right? What have we discovered from experiments upon experiments upon experiments? Well, it's that an electric current going through a wire is going to actually produce a magnetic field. And so the magnitude of that field that's produced will depend on the size of the current, and the shape of the field also depends on the shape of the current carrying the wire, right? So the way we draw the magnetic field lines will depend on the shape and the current carrying wire, right? Or the shape of the current carrying wire, right? So we might have a straight line wire, we might have like a loop kind of wire, or we might have a solenoid, which is just a wire that's twisted into a spiral. So it's like having a bunch or like hundreds or thousands of circular loops, right? So those are the three types of current configurations for wires, right? So you can either have a straight wire, right, just kind of like a cylinder, or you could have a circular loop, right? Usually we look at just one half of the loop too, just for making things easier, but a circular loop is a circular loop. And then you have a solenoid, which is basically kind of like a bunch of circular loops together, kind of a spiral. But yeah, those are the three type of configurations. Like I said, the magnitude of the field generated, the magnitude of the magnetic field generated will depend on the size of the current, right? And the shape of the field, how we draw the magnetic field lines, will depend on the shape of the current carrying wire as well. Right? So first, let's start with a current carrying straight wire, right? So just a straight wire carrying current. How do we draw magnetic field lines for that? Well, the lines formed around a straight current carrying wire are just going to be in the shape of a bunch of concentric circles, a bunch of circles around the center of the wire there. And you can test that if you have some iron fillings, put it around a current carrying wire, you see that they kind of form these concentric circles around the wire, right? But there's another question that we have to address here, and that's how do we figure out the direction of those magnetic field lines, right? Yeah, we know they're circles, but are they circles that go clockwise or counterclockwise? Well, there is that rule that I was mentioning earlier, probably the most important rule that you have to understand for this chapter and for the coming chapter as well, and that's the direction of the magnetic field. It is determined by the right-hand rule, right? So the direction of the magnetic field for a current going through a wire is determined by the right-hand rule. And so there's not an easy way for me to do this or describe this live, because any direction that I show you is going to be kind of flipped by the video. But I just took a snippet of the textbook, how they described it. But basically, you point your right thumb in the direction of the current, right? So the current's going right, you point your thumb to the right. And then you wrap your fingers around the wire in a circular kind of motion, right? And then your fingers will curl in the direction of the magnetic field lines around the wire. Now, if you were to look at, for example, a wire that's just like, imagine a wire going straight up and down in front of you, right? Well, if that wire has a current that's going upwards, right, and I wrap my fingers around it, then I can see that it's kind of going counterclockwise in that sense. If you guys all want to try that and double check with me, please let me know if you're able to kind of come up with that. So I want to see this from everyone in the chat. Just tell me if you were able to pretend that you can see a wire in front of you, right? And the current is going upwards in that wire, right? It's just vertical. And then wrap your fingers around it and see what kind of motion you're producing. Are you producing a counterclockwise or a clockwise motion? Is everyone producing a counterclockwise motion? Let me try to draw it here. So it's like, here's your thumb. I can't really draw. Like, anyway, okay, I'm hoping you guys were able to do that. But, yeah. I guess if you kind of had like your thumb like this, and then maybe if you had like your finger like that. These are like demon fingers, I'm sorry. And this is kind of tilted as well. Shoot. There we go. Yeah, these are demon fingers. And then you had this wire kind of like that, right? So your thumb should be in the same direction as the current. Current's going upwards. And then your fingers will kind of wrap around this way. They'll wrap around the wire that way, right? Does that make sense? And that would be counterclockwise in that sense, right? Does that make sense for everyone? Yes, no? Okay. Now, at the same time, another important thing is that it's not just about counterclockwise and clockwise directions. What's going to be more common for you guys to come up against or come across on these quizzes and exams and stuff is the idea of the direction being defined as into or out of the page. Into or out of the page, right? And that's just in reference of the page in front of you, like the piece of paper that you're working on. Is it going into the paper or outside or out of the paper? So if you had that wire like this where the current is moving upwards and you pretend that your thumb is pointing upwards, right, in the direction of the current, and then see if you can like have your thumb pointing upwards, right, and then have your fingers kind of curled, but have it, instead of being curled, just kind of set them flat on your desk, right? What direction are your fingers kind of going into? Are they upwards or downwards facing or into the desk? So if I drew my thumb like this, and I just had my I don't know, I can't, like I said, I can't draw. But if I'm just having my thumb moving upwards like this in that positive y direction, upwards in the direction of the current, and I just rested my fingers, right? Maybe curl them a little bit, like almost like forming a fist. But put them down on the table. What do you notice? Are your fingers going into the table or outside or up and above from the table? How are you getting out? Yeah, so hold up. Let me see if I can just like turn my camera on or something to kind of show this. So I don't know. Can you guys like see my fingers here? Right? So here's your finger. Obviously everything's going to be flipped, right? So there's your finger, and then you kind of like curl your, there we go. So I guess I don't know what direction I'm facing in. But thumbs up for the current like this, right? Flat on the table. And then you kind of wrap your fingers around as if you were trying to go through and wrap your fingers around the wire. But instead you have this table here in place. And so basically, right, this is going to be like into the page or into the desk, because you're trying to like, as if this desk was supposed to be a cylinder, right? But it's flat. It's a flat surface. As if the paper in front of you was supposed to be a cylinder, but it's a flat surface. And so here's your thumbs up going for the current upwards, and then you try to wrap around, but it's going into the page, into the desk, right? As opposed to the other way around, right? Where if I look to the left, because this is just me looking at the current to the right of the current, right? Or to the right of the, what's it called? The right of the wire. So here's the right part of the wire. Here's the left. So if I'm looking, have my thumbs up, and I'm trying to go and look at wrapping my finger around the right part of the wire, right? Or to the right of the wire, then I see that it's going into the page at this point. But if I flip it the other way around, right? Where I'm looking at the left side of the wire, I can see that my fingers are curling upwards out of the page, right? So it's kind of like here, I'm going into the page, and then if I were to come around back to the left of the wire, I'm coming out of the page like this. Does that make a little bit more sense? I mean, I don't mind turning my camera on. It's just like, it's difficult because the direction is flipped and it's not easy to kind of show you guys what's going on. Yeah, so it's not just one direction. It depends on what direction you're looking in, or like where you're located relative to the wire. So if I'm to the right of the wire, then my fingers will wrap around to be going in a counterclockwise direction, but it's also going into the page, into the desk, right? And if I come over here to the left of the wire, well, still, that's counterclockwise, right? Counterclockwise doesn't change, but I'm coming out of the page now, right? So you got to wrap your fingers around the wire and pretend you're kind of going down and out. So down and out, right? So into the page on the right, out of the page on the left. Any questions about this notation? Because it's extremely, extremely important to understand. So if I were to tell you now, if I had a wire that was like this is a horrible wire. Current is going to the right. If I looked at point P here, for example, is this going to be into or out of the page? So pretend the page now is like a wall in front of you or something. So basically point your thumb to the right and then kind of pretend to wrap your fingers around that wire. Into, excellent. So it's into the page at this point. How about here? If I said point C, how's it coming out now? Out, exactly right. So into the page at the bottom, out of the page at the top, right? Does that make sense for everyone else? Does everyone see that? So it's basically like, here's your thumb, right? And then your fingers are wrapped around like this, and they kind of curl into the page at the bottom and then curl out of the page at the top. Does that make sense? Let me show it here as well with the camera. So at least I'll try my best, because like I said, it's kind of difficult to see. So if I were to, I don't know how to like, I don't know. It's very difficult to like do this without, like the directions are kind of messed up. Let's see here. So I guess if I was, I don't know. Yeah, I'm not even sure how to like describe this and not screw up the direction entirely. I guess well, here's a wire, I guess, that I have for my iPad here, right? So if I'm saying that the direction faces, okay, you know what, screw it. That's not gonna work. It's not gonna work at all. Yeah, the direction is just flipped, unless there's a way I could, Ooh, interesting. Hold up. What if I use my phone's camera? Okay, well, here's my phone, right? Oh, this is, okay, this is dope. So if I had, gosh, okay, it's still kind of flipped. Yeah, it's still flipped. Yeah. Okay, yeah, it's still flipped. Darn. Yeah, like I'm pointing to the left, but you guys are seeing me pointing it to the right. That's a bummer. All right, it is what it is. Yeah, I know. I was pointing to the right, and you guys probably saw it pointing to the left. It wasn't inverted? Hold up. Yeah, one sec. Let me try and redo that again. Well, apparently I can't use my phone anymore as a camera. Anyway, I mean, I have some pictures to show you guys this here in a bit. I took pictures earlier today to help with this, but hopefully that roughly makes sense. Probably it'll make a little bit more sense here in a sec because I took pictures of this stuff. So, how do we determine the magnitude now of magnetic field of a straight wire, right? So we figured out the directions and stuff. Now we want to figure out the actual magnitude, the value of the magnetic field strength, right? So magnetic field is denoted with the letter B, right? So we denoted electric field as E. Now we want to denote magnetic field as B, right? So the magnetic field of a straight current carrying wire can be determined by the following equations, right? Or the following equation, but here's the constant for that equation as well. So mu 0 is a constant that relates all these quantities together, and it's called the permeability of free space. I, in this case, is the current. R is the distance away a specific point is from the wire, and then your units for magnetic field are Teslas. So units for magnetic field is Tesla. But yeah, that's how you figure out, and this is the magnitude of the magnetic field at a specific point. Now, how can we figure out the net magnetic field at a specific point when there are multiple wires? Because you're not always going to be dealing with just one wire in these examples. You could also be dealing with multiple wires. So just with like anything that we've done before, right, whether it be forces or electric fields or whatever, you're always going to be using the principle of superposition, which just means that we add up all the independent fields to find the net field, right? So like I said earlier, you're going to have your magnetic field either pointing into the page or out of the page as the notation for these problems. And that's all relative to the paper you're looking at when you're solving your problems, as I mentioned earlier. Now, really, really important is to understand that into the page is positive, out of the page is negative. I think theoretically you could reverse this, but you'd have to keep your notations constant. But I found that what the book uses and what's most consistent, what offers you the best kind of experience when solving these problems, is to treat into the page as a direction that means a positive magnetic field, and out of the page as a direction that means a negative magnetic field. So, like I said, if you look at this example, the wire on the bottom has a current going to the right, right? So if we get our thumbs, point to the right with our thumb, right? We use the right-hand rule. We can see that the magnetic field is pointing out of the page above that wire, right? So if I point, this is my thumb right here, my thumb pointing in this direction, then below the page, or below the wire, it should be going into the page, and then above the wire should be coming out of the page, right? So it's out of the page above the wire, that bottom wire at least. Does that make sense so far? Are you guys seeing that direction? You'll probably see it here in a sec. But we can also see that the magnetic field is pointing into the page below the wire, like I said, right? So into the page below the wire, into below the wire, and out of the page above the wire. for that bottom wire. For the top wire, you have your current, your thumb, pointing this way, right? Now, can someone tell me what direction the magnetic field be pointing in, into or out of the page in the bottom of the wire? Into or out of the page at the bottom of the top wire alone. Out. Excellent. Out of the page here at the bottom, and obviously it's going to be what at the top? So top of the wire here, top of this top wire. Into or out of the page? Into, right? So your thumb, your fingers wrapped around into the page, and they come out at the bottom there, right? And you'll see here with the pictures that I've taken, it's going to be hopefully easier to kind of visualize as well. But yeah, so point B, I think I put B instead of P, so let me edit that one as well. So this is point P, is above both wires. So we want to analyze what the magnetic field is above each wire alone and then add them up together, right? So at point P, it's feeling a magnetic field due to wire 1 and due to wire 2. But we have to look at each one separately, right? So in both cases, like point P is above wire 1 and it's above wire 2. So now we got to look at, okay, well, if it's above wire 1, above wire 2, what is the magnetic field direction, right, for each wire when we look at a point above that wire? So literally this point here, this point there, this point here, that point, point P, right here or right here, with respect to wire number 1, right? Wire number 1, we said that above the wire, we're pointing out of the page, right? So at point P then is feeling out of the page due to wire 1, right? But it also feels into the page from wire 2, right? And like I said earlier, into the page is positive and out of the page is negative. So if we were to kind of do this, right, and calculate B net, basically, it would look like something like this. It would be B wire 1 is out of the page, right, and that's negative, and B wire 2 is into the page, and that's positive. So it's like B wire 2 minus B wire 1, right? And it's the magnitude of both of these when you're calculating the equation. We plug everything magnitudes, and then you add your negative or positive signs depending on the direction. And so in this case, like I said, wire 2, when you're above wire 2, you have into the page. When you're above wire 1, you have out of the page. So wire 1 is negative. Here you got the minus sign, and wire 2 is positive. That's how you would figure out your B net in that case, right? So like I said, bottom wire's current tells us that any point above that wire will have a magnetic field pointing out of the page, right? So the magnetic field at point P due to the bottom wire is negative. Upper wire's current tells us that any point above that wire will have a magnetic field pointing into the page, right? So the above wire, the top one, is going to have a magnetic field pointing into the page for any point above that wire. And so the magnetic field at point P, since it's above that wire, is positive, right? So the magnetic field due to the, I think I had bottom wire again here. This should be top wire. Sorry for all the typos, but it should be positive. So this top wire should be positive, or the upper wire, right? And so these are the directions, these are the pictures that I took to kind of help explain a little bit more. So this is the magnetic field for the bottom wire above the wire, right? So we had wire 1 and wire 2, right? And so this one had a current pointing this way, and this one had a current pointing to the left. So this is to the left up top and to the right at the bottom, right? So my thumb was pointing to the right, And then if this, like I could think about my thumb as being this wire axis, and this is above and this is below the wire, right? So if I did that, I can see that above the wire, my fingers are pointing at me, towards me. If this was the page, if my desk was the page, then I'm going out of the page at the top, right? I'm going out of the page above that bottom wire, wire 1. So I'm putting out of the page, above the wire. Now, once again, here's kind of my thumb is supposed to be pointing in the direction of the current, so the current was pointing to the right. I can think about my thumb and the rest of my arm as being this like wire axis, right? So now I'm below the wire. I can see that it's pointing towards the wall or into the page, right? So this is into the page for that bottom wire, right? So effectively what I did here is I basically like wrapped my finger around the wire. So I rotated kind of my wrist to basically try and orient myself in different ways to show that it's coming out of and into the page, right? So this, or it's not even like really rotating your wrist as much as it is like, because this right here is kind of pointing upwards, like I said, but this orientation was more me like moving my entire arm. So it's more like a motion of the elbow, kind of. But basically, you should be able to see that when you're looking below here, right, it's pointing into the page. If you were to try and kind of rotate your wrist and curl your fingers around the wire, right, curl it upwards, you should see that your fingers would then come back at you, right? So if you start in this position, right, if you start in this exact same position here, you see that this is the wire, here's the current following the direction of my thumb, here's below the wire, here's above. If I wrap my fingers around, I can see that everywhere below my thumb, everywhere below the wire is going to be pointing into the page, into the wall. As soon as I start wrapping my fingers around, like I just kind of like rotate my wrist a little bit, or rotate my fingers, wrap my fingers around this way, they should curl, and as they curl upwards, and then they come towards me. My fingers would come towards me. And so at that point, your fingers would kind of be above your thumb, and that would be kind of like above the wire. And so when it's above the wire at that point, you see your fingers coming towards you, that means you're out of the page at that point, right? So now my fingers would kind of be pointing towards me, away from the wall, right? If we did it for the upper wire as well, the upper wire is pointing to the left, so you have current, right? There's my thumb wire axis right there. This is above and this is below the wire. You can see that my fingers would kind of wrap around or try to curl into the desk. So this is into the page. They're trying to curl into the desk, into the page, into the wall, right? But as soon as I try to curl them, right? As soon as I try to curl my fingers downwards, if this, well, I kind of took two different shots, but it's fine. Basically, if I were to be able to curl through the desk, right, or through the page and come back around, then I should see that at the bottom of the wire, right, or below the wire, my fingers should be pointing away, right, or towards me, or out of the page. Right, so this was the wire here with the current to the left. Then my fingers would wrap around to be out of the page, out of the wall, right? Away from the wall or away from the desk or from the page, and then towards me. Does that make sense so far? Do these pictures help clear things up? Sound good? Yes, no, give me some thumbs up or something. Okay, I see a thumbs up. All right. Now, that is probably going to be the most important like set of hold up, give me 1 second here. I just need to charge my computer real quick. Let me just orient myself this way. I'm sorry about that. I gotta plug in the charger. Okay, there we go. Yeah, so with the straight wires, I think those are probably going to be the most important, probably going to be the most relevant when it comes to trying to figure out the directions like into and out of the page and stuff. The next two, the circular loop and the solenoid, from my experience, I don't think it's as important. I haven't seen like a whole lot of ones that would be asking you. Maybe I think it's more the solenoid than anything else that's not going to be as common. The circular loop I think is more common. So to draw magnetic field lines for a current carrying loop, you need to know the magnetic field within a current carrying loop is stronger than the outside of the loop first, right? So within the loop here, you can see that the lines are much more closer together as opposed to outside of the loop. They're more spaced out. So the magnetic field is stronger inside the current loop, which kind of makes sense, right? And so we can draw these magnetic field lines once again with the help of the right-hand rule. But the issue is that you have the current direction kind of varying as you go through the current, or as you go through the loop, right? So if I were to try and use my thumb, right, it's kind of pointing to the left here, but now my thumb is kind of pointing down into the left here and directly downwards here, and now it's kind of pointing to the right here, right? So the direction your thumb points in kind of changes as you go through the circle, and so based on that, your what's it called? What do I want to say? You kind of have to reorient your hand around to basically figure out whether the inside of the loop, like within this inner loop here, if it's pointing into the page or out of the page, and then the outside parts here, if they're pointing into or out of the page. So you just kind of have to reorient your hand and curl your fingers around in different directions to be able to figure out the magnetic field direction, right? So here they kind of had their finger or their thumb here pointed to the left, right? And then imagine like if you were holding up or like carrying a briefcase or carrying a bag or something, then your fingers would wrap around like this, right? And then this would be kind of pointing out of the page towards you, right? Be pointing out of the page. Everywhere in the middle of the circle here is pointing out of the page, right? So if we were to grab our thumbs again, right, and then basically kind of like curl our thumbs around to like wrap around and go through the middle of that loop, you should notice that your thumbs or your fingers kind of wrap around in a way that the fingers go out of the page, right? Right. So if I have my thumb here and my fingers were to wrap around this way, then they wrap into the page on the left-hand side here and then out of the page on the right-hand side. Right. So just kind of wrap it around and then hopefully you can see that. Now, I think I'm going to mention this later, but it's probably important to mention now anyway. These dots signify out of the page. Whenever you see a circle with a dot in the middle, that means out of the page. Like that direction should be out of the page. When you have these X's, it means into the page. So that means everywhere outside of the circular loop is into the page, and then within this circular loop, like in the middle here, it's out of the page at this point. Another way that they kind of draw these circular loops is instead of just having like a loop like that, they might draw it kind of as a wire like this, just as a straight wire like that. And so what they want you to realize is that they have this circle with a dot in the middle. That means it's pointing out of the page here, and a circle with the X in the middle. That means into the page. Now, when they draw it like this, they're not referring to the magnetic field. They're referring to the current coming out of the plane, right? So they're telling you basically like the current is coming out of the page here. This is out of the page, right? And going into the page at this point, right? So if I were to have like a wire like this with a circle and a dot here and then a circle and an X there, this should be pointing out of the page. It should be pointing into the page, right? So if you were to think about this and kind of think about this, okay, here's a circular loop, then if this is out of the page, that means the current is pointing upwards like this, like that, and then into the page this way, right? So in a sense, this is kind of like saying that your current is going clockwise almost, right? If we were to reverse it, right? If we were to reverse it and say that, okay, well, I have X here and a dot here, well, then this is out of the page, and this is into the page. So my current, everywhere around here is going to be kind of in a counterclockwise position, right? Now let's see if that affects whether, like within my loop or outside of my loop, if that affects my into and out of the page directions for my magnetic field. So if I had, once again, the loop going this way, right, where this is out of the page and this is into the page for the current, then the current kind of points this way, right? If I were to wrap my fingers around this loop like that, if I imagine like carrying a bag, right, my fingers should point in which direction here? Into or out of the page? Like within this circular loop, in this region here, in this shaded region. Am I pointing into or out of the page? I see into. Who else thinks it's out or into? So I think it's out, right? Because your thumb would kind of go this way, right? And forgive my drawing, but your fingers would actually kind of be behind this loop and they would kind of wrap around to go outside of the page in this middle part. Now, for those that kind of missed this earlier, like if I thought about, okay, here's my current going to the left there, right? Let's say it's kind of hard here because I have a flat surface like a desk or something. Or actually, hold up. Yeah, here it is. Here, this one. This was a better one. If this was my circular loop here, where my current is going that way, right? Then you see that this shaded region here, that shows that my fingers would be curling away from the wall, right? Towards me. That's out of the page. Like if you imagine this wall was the page, that's pointing away from the page or out of the page as opposed to into the page, right? Does that make sense? Okay. Now, if I had the same current moving this way, right, to the left like that, along that same kind of circular loop, then everywhere outside of the loop would point what direction? Into or out of the page? Into, exactly, right? So basically, your thumb kind of point this way, right? And then your fingers, once again, forgive my drawing, I hate drawing, so they would kind of wrap around this current right here, this wire, and they would kind of go into the wall, into the page. But yeah. If we were to have now, like I said earlier, if I said the current was, oops, did I say, hold up, which direction did I have? Okay, I had it this way. This was out of the page here. So I'm going to make this into the page over here. And then this is out of the page. And remember here when we're talking about circular loops and they have this notation like that, they're talking like into and out of the page for the current. So that way, current is pointing out of the page like this and into the page on this end right here, right? So if the current is going this way, am I into or out of the page in the center here? So at first it was going to the left, now it's going to the right for my current. So am I into or out of the page in the middle of the circular loop? Into, right? How about outside here? out, right? And we can double check that by looking over here. If this was my circular loop, my eye is pointing this way, here's my fingers wrapping around it, right? And that would go into the wall, into the page. Does that make sense? Okay. That's the idea there. Like I said, pointing into the page is denoted by little X's, pointing out of the page is denoted by little dots. And let's see here, what else? So, yeah, and I already mentioned this earlier, is that into and out of the page is just talking about how the magnetic field would point relative to the piece of paper we're solving the problems on. Now, if we wanted to figure out the magnetic field strength of that current carrying loop, right, circular loop, then we'd use this equation here, where the magnetic field is equal to the permeability of free space, constant, times the current of that wire, and then divided by 2 times the radius of that circular loop. Or we could also just divide by the diameter here, either one. Now we get to solenoids, right? We get to solenoids here. And so solenoids, like I said earlier, they are basically just a bunch of loops together, right? A bunch of current carrying loops, like we're talking like hundreds, thousands of current carrying loops. And so larger number of turns will cause the field inside to be even more uniform and have a larger strength, right? So the more like circular turns you have, the larger the electric field, or the larger the magnetic field strength, and it causes the magnetic field to be more uniform in the middle, or the inside of the solenoid. And then, like with a circular loop, your field is uniform on the inside, but the field outside is noticeably weaker, right? So if you remember, with a circular loop, things inside were kind of tightly spaced or tightly packed, but on the outside, they were more widely spaced, and so they were kind of weaker on the outside, which I guess that kind of makes sense, right? And like we said earlier, like you should have a stronger magnetic field closer to the magnet itself, or in this case, closer to the current or the wire, and then as you get farther away, it would decrease in strength. But yeah, and then, like I said, solenoids, I don't think it's like absolutely essential to like know everything about how to draw them and stuff, because their magnetic fields are a little bit more confusing to draw. More common is the circular loop and the straight wire stuff. But for the magnetic field of a solenoid, you can use this equation to calculate it out. So this is the permeability of free space constant times the number of turns, right? So it's like the number of like circular loops, basically, or the number of turns, and then multiplied by the current going through the wire or through the solenoid, and then divided by the length of the solenoid, right? There is a special circumstance or a special situation in which the length of the solenoid is very small compared to the radius. If that's the case, if the length and the radius are kind of similar to one another, or actually not similar, if the length is very small compared to the radius, like I said, then you can use this equation instead. Oops, I don't know what happened there. Yeah, you can use this equation instead, basically. But that's pretty much everything you need to know for magnetic fields. But what about magnetic forces? Well, magnetic forces will still kind of focus on the right-hand rule, but it's a different version of the right-hand rule. And so to start off, we got to explain what magnetic forces really are, right? Well, we kind of talked about electrostatic forces before, electric fields before. Now we're talking about magnetic forces and magnetic fields. They're all kind of similar concepts. And so once again, magnetic fields, like electric fields, will be able to exert magnetic forces on magnets or other objects, right? And magnetic fields could also exert forces on moving charges, similar to how an electric field can do that for charges, right? Now, how do we determine the direction of magnetic forces? We use another right-hand rule like we did for the magnetic fields, right? In this case, the right-hand rule that we use is not wrapping our fingers around like a current-carrying wire or something like that. Now we're interested in looking at a couple things here. So, number one, your thumb acts as the direction of the particle that we're interested in, right? It describes the motion of that particle, if it's moving upwards, downwards, left, right, at a specific angle, etc., right? Your index finger points in the direction of your magnetic field, and then your middle finger points in the direction of your magnetic force, right? So they should all kind of be perpendicular to each other. You should hold your fingers up in a way that they're perpendicular. Like, don't make your middle finger really close to your index finger, like right here. We always have to have them like at right angles to one another, right? So it's almost like you kind of, I guess it's self-explanatory. Right angle here, technically a right angle there, right? And then between the thumb and the middle finger, it's a right angle as well. So kind of make that motion right there with your thumb, index finger, and your ring finger. Now, we're often going to be dealing with like knowing two of the directions, and we're looking for the third, right? So we might know the direction of the particle, we might know the magnetic field's direction, like into and out of the page, and then we just need to figure out the magnetic force direction, right? So let's say, for example, you had your magnetic field pointing into the page, right? So into the page. And then you had your particle moving upwards, right? What would be the direction of your force? So into the page is just like point away from you. Out of the page, we're pointing towards you, basically. So if I'm pointing away from me, that's my magnetic field. Into the page, I have my thumb, my velocity moving upwards. Exactly. I should have my magnetic force pointing to the left. Exactly. Now, here's where things get like a little like carpal tunnel-y. If you try now to think about, okay, what if the magnetic field is pointing towards me, right? What if the magnetic field is pointing towards me, but my particle's still moving upwards? Then what direction does my magnetic force point in now? To the right. Exactly. Right? That's it. I don't think I want to say anything else about that. Let's see here. What did I want to say after this? So yeah, that's pretty much it for the right hand rule there. It's pretty self-explanatory, but it's just kind of hard to move your fingers around and stuff. But I guess if you ever wanted to like secretly flip someone off, you could just say you're doing the right hand rule. So I think we did that. We did our fair share of that in AP Physics in high school. So you try to flip someone off, you're like, oh, no, I'm just doing the right hand rule. But yeah. Okay, so how can we calculate the magnitude of the magnetic force now? Well, it's going to be dependent on a couple things, namely the magnitude of the charge feeling the magnetic force, the perpendicular component of the velocity, right, of the charge. So once again, the velocity, magnetic force, magnetic field all have to be perpendicular to one another. If the velocity isn't quite perpendicular, right, to the magnetic field, then it'll have a perpendicular component, right? So if your velocity is like this, for example, then we're just looking, and let's say your magnetic field is pointing this way, your B is pointing that way, right, upwards. Then we're interested in like V perpendicular. Like if you had V right here, you take like V cosine theta basically, or something like that, to figure out the perpendicular component of the velocity. But that's something that's kind of rare. We don't usually do that. Usually everything is going to be given as a perpendicular component built in. Like I said, yeah, so velocity is going to be perpendicular usually, so we don't have to do any trig calculations. But if you do, or if the velocity is not at that perpendicular angle, then just know that you basically just have to figure out the perpendicular component, right? Not the parallel component, the perpendicular component. And then the last thing that magnetic force is dependent on is the magnitude of the electric field. So it's the magnitude of the charge, magnitude of the electric field, and then multiplied by your velocity, right? So there's one thing to watch out for, and that is the fact that there's a difference between positive and negative charges, right? So you could have a proton or an electron as your particle, Once again, the convention, like I was talking about a lot in the last couple of chapters, the convention is that we're dealing with positive charges. So your right-hand rule will always give you the correct direction for a positive charge. However, right, it's only accurate for positive charges. What if we ever had a negative charge? Well, then whatever direction, like let's say you're looking for the direction of the magnetic force, right? If the direction with the right-hand rule is pointing to the left, then just take the opposite that, and that'll give you the direction that an electron would be pointing in, right? Or the direction the magnetic force would be pointing in for an electron. So if I do my right-hand rule and I see that my magnetic force is pointing to the left, right? Well, then my magnetic force for an electron would be pointing to the right instead, right? So that's the idea there. You just have to flip that. So just don't forget that for electrons or negative charged particles, everything is flipped for the right-hand rule, right? I don't know. Let's say you were trying to find the velocity of the particle. Let's say you know that the magnetic force is pointing to the left, and the, let's say, magnetic field is pointing away from you, right? Or pointing towards you, my bad. So out of the page, towards you. So if the magnetic force is pointing to the left and the magnetic field is pointing towards you out of the page, then your velocity, right? Your velocity will be pointing downwards, right? But for an electron, exactly, I believe it should be upwards in that case. So you just flip it for an electron. Does that make sense? It's kind of weird, I know. I'm fairly certain that's the case for velocity. Usually it's only that they're asking you about like the magnetic force, like direction and stuff. So if we know the velocity is upwards and we know that the magnetic field is pointing into the page, for example, so index finger is away from you, your thumb is pointing upwards, then the magnetic force will be pointing what direction for a positive charge? So thumb pointing upwards for velocity, index finger for magnetic field is pointing away from you into the page, and then your middle finger, your ring finger, is pointing in what direction for your magnetic force for a positive particle. Left, right? And if it were for an electron, then it would just point what direction? Yep, exactly. If we keep the same direction if it's positive, if it's not positive, it's negative, right? Then we just flip the direction. Yep, change direction if it's negative. That's the basic idea there. And then we get to trajectory of charged particles in a magnetic field. So those particles will have a specific trajectory. They'll move in a specific way. And they tend to move in a centripetal manner. They tend to kind of move in a circle. And so that's because the magnetic force on the charged particle is always perpendicular to the velocity, so that the particle then has zero tangential acceleration. So magnetic force will only thus contribute to centripetal acceleration, right? And so that means then our centripetal force, this is getting back into physics 1 concepts, is equal to our magnetic force, and that's equal to mv squared over r, which is the centripetal force equation, right? And then we can set that equal to the magnetic force. Why is this useful? Well, it helps us figure out exactly what kind of centripetal motion we have. Like how big is the circle, or how big is the spiral are we moving in? Or, yeah, that's really honestly pretty much it. Like figuring out if we are moving in a very kind of like tight spiral, or if it's more kind of like a gradual kind of spiral. Like if it has a larger radius or if it has a smaller radius based on its force and centripetal force. So if we rearrange this equation, right, we come up with mv over qb is equal to the radius, right? So the radius of uniform circular motion of a charge in a uniform field. So, yeah, this would help us basically figure out the radius of the uniform circular motion, right? help us basically figure out the radius of the circle that the particle is moving in, if it has a uniform magnetic field. And for this equation, we use the absolute value of the charge, by the way. Now, this equation tells us that if the particle speed increases, right, if the v goes up, we would need a large force to keep it going around a circle of the same radius, right? So if we increase v, then the force has to increase in order to keep the same radius, right? Or alternatively, right, if the v increases, right, we'd have to decrease the radius, right? If we increase the speed, then we would need, or hold up, did I say? I said decrease the radius, my bad. It shouldn't be decrease the radius. We should also have to increase the radius in order to keep the same magnetic force, right? Because if this increase in speed or increase in velocity causes an increase in the magnetic force, then an increase in the radius, increase in the denominator, is going to decrease that magnetic force to bring it down to its original value. So if we increase particle speed, we would have to increase the radius to keep the same force, right? That's what the equations tell us as well. And then these are kind of descriptions here of the circular motion that you experience with a particle in a magnetic field. It'll move in this centripetal motion kind of direction, right? So we were to test this out with our right-hand rule. We have velocity, right? Our thumb is pointing upwards. Our B, our index finger, is pointing into the page. That's away from us. And then we could see that our magnetic force should be pointing to the left at this position, right? Well, we also could look at this position. That's kind of a little bit harder. But if we were to kind of point, I don't know, that's kind of like velocity pointing down into the left, right? So our thumb should be kind of pointing this way, and then your index finger should be pointing into the page, right? So try to do that with your fingers, kind of some acrobatics here to do it. But velocity is down into the left, B, your index finger still into the page, and then what kind of direction is your magnetic force, your ring finger? What direction is that pointing in now? Like this should be your index finger here into the page. So I kind of did it dotted so it can show that it's into the page. But what direction should your ring finger for your magnetic force be pointing in now? So if you kind of tilt your thumb to be down and to the left, still have your index finger pointing away from you into the page, then your ring finger should be pointing in what direction? Down and then just directly downwards, or is it kind of tilted a little bit? What's going on here? Is it like down to the right, down to the left, directly downwards? What direction? If your thumb is kind of down and to the left, index finger is pointing away from you towards into the page, and then, yep, exactly, down and to the right. So this should be your middle finger there, down and to the right, which makes sense because here is down to the right, right? So we said the velocity is kind of down and to the left. Your index finger is into the page, right, away from you, and then your ring finger should be kind of down to the right if you were to do the right hand rule for that, right? And then this is kind of what I was talking about earlier with the spiral, right? That's how the particle kind of move, because you'll have at that point, like, you have a perpendicular component to your velocity as well as a parallel component, and so it'll kind of just move in this direction like that. But yeah. And then lastly, I think this is the last topic pretty much, is how can we calculate the magnetic force on a current carrying wire, right? So we look at a specific wire, we want to figure out the magnetic force on it, not by it, on it, right? So we use this equation here, which is we calculate the current, or the perpendicular component of the current, right, of the wire, and then times the length of the wire, and then times the magnetic field, right? So let's see here. Most important thing is that, once again, we're looking at the force on a specific wire, right? So we're just interested in one specific wire here that's going to be carrying some current, right? That's supposed to be perpendicular to the magnetic field, right? So the current is to the right, magnetic field would be upwards like this, right? And so we also multiply by the length of that specific wire that we're interested in, and then we multiply by the magnetic field. Which magnetic field is this? Is this the magnetic field that's generated by that wire that we're looking at, or the magnetic field that's felt by the wire that we're looking at? Well, since we're looking at the force that that wire feels, we're interested in the magnetic field that that wire feels at that point, right? And that might be generated by other wires, right? So let's say we have two wires. Well, then we would look at the magnetic field generated by one wire and then analyze how it affects the other wire, right? So we look at what that other wire feels with respect to the first wire's magnetic field, right? Length would just be the length of the wire that we're analyzing. And then if we had another wire here, this is I1, wire 1, this is wire 2, right? Wire 2 is going to be generating some kind of magnetic field. Might be just directly upwards like this, like we talked, right? When we calculate the magnetic field of a current carrying wire, right? Remember we did that earlier. Where's that? Here we go. You use the current then of the wire that's generating that electric field, or that magnetic field, my bad, the current of the wire that's generating that magnetic field, and then the radius, or the distance we are from that wire, right, at a specific point. And that specific point is that second wire that we're interested in, right? So if we start off, here we go. So here's wire 2. Then I would use, for my magnetic field equation, I would use the current, the I, for wire 2, and I would use the radius as basically the distance I am away from wire 2, which is the distance at wire 1, basically, right? So they might tell you this is like 4 centimeters or something, so that's my R for my magnetic field. And so that magnetic field is the magnetic field felt by the wire we're analyzing, and in this case we're analyzing wire 1. Right? And then length is the length of the wire that we're analyzing. So we're not using this length, we're using the length of the wire that we're looking at. And then, yeah, that's pretty much it for the magnetic force that a wire feels. And you could look at page 25 for like a little bit more detail, more background about a specific problem like this one. And then the reason why we're looking at the perpendicular component of the current is that, for example, you could have this wire kind of tilted at a specific angle, and so you can't just plug in the current like that. You have to actually plug in the perpendicular component of the current. So it's like taking I cosine theta, right? So cosine would give you this adjacent I perpendicular here, which is perfectly perpendicular with the magnetic field, which is pointing upwards, right? So in that case, you could do I LB cosine theta to figure out the perpendicular component of the current. Now it doesn't always have to be cosine. It could be sine, because what if I told you that it was this angle that we were looking at, for example, right? Well, then the perpendicular component, right, is this one right here. This is the perpendicular component, because the B, the magnetic field, is pointing upwards, and then this is pointing to the left like that, right? And so in that case, it would actually be sine theta, right? So it just depends on the angle that you're looking at. Essentially, you just want the perpendicular component of the current. And that's pretty much it for the week 12 content review. I've outlined some important problems here that I think you guys should look at from the practice problems in the reading. These I think are going to be extremely important, extremely important. Like, it's not even a suggestion at this point. It's almost like a command or a demand. Like, please review these questions from the reading, because I guarantee you'll see something, some concept, some similar problem, something applied or taken from those problems that's going to pop up in the quiz. I promise you. But yeah, if you review those problems, and even review extra ones from the reading, I think you should be in solid shape, in addition to looking at my PowerPoint slides and rewatching this video for those that have missed out on the first part of it. But I think that's pretty much it. That's all I wanted to cover tonight for the content review. If you guys have any questions about this stuff, please reach out and I'll try to answer as quick as I can, and as best as I can. But I think we'll probably just call that a night for this session. I will end the recording here and then upload this on YouTube as soon as I can. So I want to thank you guys for joining me for the session tonight. Thank you for those who were able to make it out on such short notice. I was not 100% sure if I was going to hold the session tonight because I was kind of rushing to finish this PowerPoint slide. But yeah, hopefully you guys benefited from it. And hopefully those who are going to watch it on YouTube as well are going to benefit from it. But yeah, that's been it.